All right, let's get started. So I would like to introduce Professor Chris Impey. He is a distinguished professor of astronomy at the University of Arizona, as well as a popular author. His research interests include black holes and observational cosmology. As an author, he has published numerous pop science books, including The Living Cosmos, a nonfiction work about astrobiology, and How It Began, A Time Traveler's Guide to the Universe, which covers what is known about the origins of a vast number of cosmological objects, ranging from the moon to the entire universe. Professor Impey was elected a Legacy Fellow of the American Astronomical Society in 2020, among numerous other accolades and honors. He received his PhD at the University of Edinburgh. Professor Impey would prefer if we saved our questions until the end, so if you have a question, feel free to stick it in the Q&A function located at the bottom right, and he'll get to it once his talk is over. So without further ado, take it, Professor Impey.
Okay, thanks very much, and I'm delighted to be with you. Not physically, that would be nicer still, but happy to be here virtually. And my topic tonight is black holes, and the title, Einstein's Monsters, refers to the fact that Einstein, whose theory, general relativity, predicts black holes and explains in significant part their properties, didn't really believe they were real objects. So the sort of theme I want to explore tonight is the fact that even though we do understand quite a lot about black holes, we've learned a lot in the last half century of research, there's a lot we still don't know, and it's a very active research field in astronomy. And I'm going to introduce along the way, of course, the two iconic figures in physics and astronomy who are the fathers of black holes, essentially Albert Einstein and Stephen Hawking. And we can start with the history of the idea of a black hole, which actually goes back quite a long way, over 2 centuries. John Mitchell, an amateur astronomer and clergyman in England in 1783, and Pierre Laplace, French philosopher and physicist, speculated that there might be a star dense enough or large enough to have an escape velocity equal to that of light. And so logically, it would be a dark star. So the idea was out there 200 years ago, a century before general relativity. In 1800, Thomas Young demonstrated the wave nature of light, and that essentially killed the idea because nobody could think physically how light as a wave could be trapped by gravity, whereas when light was a particle, which was Newton's corpuscle idea, it would seem perhaps plausible that the particles could be trapped. So this idea essentially lapsed until we had a better theory of gravity. And so we have to enter Einstein's world to understand black holes and see where the idea really comes from. Well, Einstein needs no introduction. He gets a round of applause because, of course, he was an iconic figure in the history of science, arguably the greatest scientist who ever lived, certainly the greatest physicist of the last century. And it's his theory of gravity from 1916 that leads to the idea of black holes and is still our currently best theory of gravity. Einstein was struck by a coincidence that the inertial mass, which is the resistance of an object to any change in its motion, is identical to the gravitational mass, which seems to be quite different. That's just the change in motion due to the force of gravity. In the modern physics world, this equivalence is accurate to 15 decimal places, so it's really identical. But he saw this coincidence as suggesting a deeper meaning, and it impelled him towards an idea where there was no way to distinguish between acceleration caused by gravity and acceleration due to any other force. And he framed this in 2 thought experiments. In the one you see here, he imagined that someone trapped in an elevator or a lift in a rock on the ground, stationary, would not be able to tell where they were. They would drop objects and study their motion. And that would be identical to a situation of someone in a rocket on the left accelerating at 9.8 meters per second. And he speculated there was no way that these 2 people could tell their situation or that they were different. And yet one clearly involves gravity, the Earth, and the other just involves the acceleration of a rocket. It could be in deep space with no gravity. Another pair of situations are also equivalent. On the right, someone is floating in deep space in a spaceship with 0 gravity, not feeling any weight. And on the right, someone is in a much more ominous situation of being in an elevator or a lift that's cable has broken and they're plunging to Earth. And they would also seem to be floating within the cage that was plunging to the Earth with that acceleration. And he said there's no way you could tell between these two situations. And so these two thought experiments were what impelled him towards a very different formulation of gravity. And what he came up with mathematically by reaching for mathematics of curved space-time and multidimensional space-time, which really came from pure mathematics of the mid-19th century. He pulled that math and developed physical theory based on the idea that mass and energy, which he had hyphenated, of course, with his famous equals mc squared equation, curved space and time. And those two things, which were independent and really quite different from each other in Newton's theory, are now hyphenated in Einstein's theory. And so we have the idea of space-time. And today's mass energy curving space-time, in a nutshell, is general relativity. And we've had so many demonstrations of it. One of the most successful physical theories we have. Here's gravitational lensing seen by the Hubble Space Telescope. The bright galaxies in the center are acting as a physical mass lens that is distorting light from distant galaxies and turning them into little arcs that form circumferential distorted images at the edge of this Hubble image. We've seen thousands of examples of this, and this lets you weigh the cluster and show that the universe contains mostly dark matter. But the premise that mass can bend light is vividly demonstrated by many, many images in astronomy now. We also know, and this has been demonstrated too in the lab, that gravity slows down time. And in principle, at the point where we would have an event horizon of a black hole, all matter, all energy, all information is trapped, and time actually stops. Time would stop to go to a standstill at the event horizon of a black hole. So that's a prediction of general relativity that's been confirmed. So how do you make black holes? So in principle, anything can be a black hole. If you sufficiently compress matter, for example, the Earth to 2 centimeters or 3 centimeters in size, it would be a black hole. If you compress a star like the sun to a few kilometers in size, it becomes a black hole. And so nature could make black holes of any size, and it was left to astronomy to decide whether or not black holes actually exist and what kind of black holes the universe contains. The first instinct towards black holes being real and finding them was from the theory of stellar evolution. So in the 1930s and 40s, people working out the life story of stars decided that the end of a massive star's life, not a star like the sun, which will die and leave behind a white dwarf, but a star quite a lot more massive, maybe 10 times the mass of the sun, will lose some of its mass along the way. And in the end, its gravitational collapse, when all energy sources are exhausted, will crush the core to what is a black hole. So that was a prediction from the 1930s and 40s from the same physicists who developed the theory of nuclear fusion and also the theory of how you make a bomb. It was people working on the Manhattan Project like Hans Bethe who actually did these calculations, and Robert Oppenheimer. So black holes are very simple. In concept, they consist of an event horizon, which is not a physical barrier. It's not a boundary, except in a sense of information. It's an information barrier where not even light can escape from inside that region. And in the theory, the center of a black hole is a cusp of mass density called a singularity. Now that's an infinite mass density, and that's a problem. So right from the outset of black hole theory, it was understood that the prediction of a singularity is a problem for the theory, because any infinity in physics means you don't understand something. So this has been a problem that's been around for a long time, the nature of the singularity, and does a black hole actually contain a singularity when, of course, that place is hidden from view. The first black hole to be confirmed was 1969, Cygnus X1, the brightest X-ray source in the constellation of Cygnus. These are artists' impressions, of course. You can't see an isolated black hole because by definition it's black, but most stars are in binary or multiple systems. And so if a massive star that's died and left behind a black hole is in a binary system with a less evolved visible star, it will siphon material from the visible star into a hot accretion disk, which you see glowing around the star, around the black hole. At the center is a black hole. The black hole is black, but the region around it contains accelerated and heated material, which will glow in X-rays because this material is very hot, millions of degrees. And along the poles of the spinning black hole, particles can be accelerated, a plasma, and twin jets will be coming from the poles of this system. So that's what was predicted. In 1969, the evidence became convincing that this one system included a black hole. And since then, about 50 similar binary systems have been shown to almost certainly contain a black hole. You don't see the black hole, but it's a binary system. You measure the orbit and use Kepler's law to deduce the mass of both members of the system. To go further, you need more theory. And this theory comes from Stephen Hawking, who's just lost to us a few years ago, but made significant progress on the theory of black holes. Stephen Hawking is another iconic figure in the history of science, also one of the greatest scientists of the last century. And he talked about the properties of black holes. So let's get a slightly cartoonish version of this.
Space-time is almost impossible to contemplate because our entire sensory existence is limited to the 3 dimensions of everyday experience.
Holy macaroni!
The easiest way for us to enter Einstein's universe is to imagine space and time to be like a sheet of rubber.
If space-time were empty, the sheet would be flat. But massive bodies like the Earth and Sun will bend the sheet and cause it to be curved.
This curvature is Einstein's concept of gravity. The more mass a star or planet has, the more steeply it bends space-time around it, and so the more gravity it has. Throw something extremely heavy like a collapsing star onto the sheet, and you soon end up with a universe full of holes.
Ow! Watch it, Cody! Oops. As the massive star cools and shrinks, it will curve the spacetime around it more and more. Eventually, when it shrinks to a certain critical size, it will quite literally create a black hole in spacetime. Things can fall into a black hole, but nothing can get out.
Oh, there's so much I don't know about astrophysics. I wish I read that book by that wheelchair guy.
The most terrifying concept in astrophysics lurks at the bottom of a black hole: the singularity. Everything that has ever fallen into the hole is destroyed at the singularity, crushed into a pinpoint of infinite density and infinite smallness. Even space and time are squelched out of existence. All that remains in the outside universe is a perfect sphere of absolute darkness, a gravitational ghost of the star that died. This sphere is called the event horizon, and it marks the edge of the abyss.
So one of the insights of Stephen Hawking was the fact that black holes, in his theorizing, this has not yet been confirmed, are not black. He imagined a process whereby at the event horizon of a black hole, the particle-antiparticle pairs that come in and out of the vacuum all the time, in the vacuum of space, and in the lab we can see this process. If this happens near the event horizon of a black hole, there's a finite chance that one member of the pair will be lost inside the event horizon and the other will escape. Since this pair processes come from the vacuum of space, the net effect of this is that the black hole loses equivalently radiation or mass. And so the black hole has a temperature, the Hawking radiation, and it has an evaporation process, which is very slow. And so this means black holes are not eternal. They radiate, the temperature is tiny. For a stellar mass black hole, it's about a billionth of a Kelvin, and they'll eventually evaporate. And for a stellar mass black hole, this time scale is incredible. It's 10 to the 69 years, so fantastic amount of time. So neither of these predictions have actually been confirmed experimentally. In fact, they may not be confirmable in any foreseeable future, but this is what Hawking's theory has predicted. He also pointed out, and others have discussed heavily since then, what's called the information paradox, that black holes have a lot of entropy or disorder. That's because the number of equivalent physical states within the black hole is very large. So the entropy of a black hole, the mass of the sun, is 100 million times the entropy of the sun itself. And this leads to a paradox because quantum theory says the information of particle interactions is always preserved. And that's a problem because at the event horizon, that information does not seem to be preserved, be lost. And so this is the basis of the information paradox. To avoid this, people have speculated that information may somehow be coded onto the event horizon. This is called the holographic principle, or that the correlations that quantum theory suggests must exist are somehow destroyed. And this is a mechanism called a firewall. And again, there's no evidence or data to distinguish these ideas, but the information paradox seems to be a real problem that needs to be resolved. Meanwhile, astronomers had found that stellar mass black holes, massive stars who die and collapse their cores, are one type of black hole, but nature knows how to make other black holes. And here you see a spectrum ranging from black holes from dead stars that are a few times the mass of the sun, up to massive, supermassive black holes, millions of times the mass of the sun. And so this is an incredible result, the fact that nature makes black holes with a range of actually about 1 billion in mass. And this is research, of course, of the last few decades. And it turns out that our galaxy has one of these black holes. So here you see an animation from research of the UCLA group working at the Keck telescope, which shows the orbits they measured for stars very near the galactic center, Sagittarius A star, which taken together are compelling evidence of a 4 million solar mass black hole in our galaxy. So this is a fantastic result, and it was work of several decades. Also, the same data was gathered by a group based in Germany at the Max Planck Institute using a telescope at the European Southern Observatory, and they agree with each other in detecting this massive object. And some of the stars that go close to this black hole go extremely close, you know, within a sort of solar system scale of the black hole. And with luck and with future observations, it's hoped that there may be stars observed which actually are shadowed by the black hole or go behind the black hole or are devoured by the black hole itself. So future observations are going to continue this work. And just to summarize, I would say that the best evidence for any black hole in the universe is actually this black hole in the center of our galaxy. It's better evidence than any of the binary system stellar mass black holes. For example, data on these stars that pirouette near the central black hole show the precession of the perihelion, which was the very subtle phenomenon in the orbit of Mercury that was used to show that general relativity was the necessary theory of gravity a century ago. The same phenomenon occurs on a more dramatic scale and with much larger amplitude for stars orbiting the black hole at the center of our galaxy. So once again, general relativity is demonstrated in this system. Also, we've had incredible success in the last few years by looking at an even more massive black hole, several billion times the mass of the Sun, at the center of the M87 galaxy. So you zoom in to the M87 galaxy, distant tens of billions of light years. Famous image now, iconic image, was taken by the Event Horizon Telescope, and a collaboration that includes a dozen of my colleagues here in Arizona and one of our telescopes on Kitt Peak. This is the first ever image of any black hole. It's the shadowing, of course, of the event horizon and the very hot gas around the event horizon. The distortions and the asymmetry are all as predicted by general relativity. So once again, this is a great affirmation of our gravity theory, but also spectacular to be able to get a very first image of a black hole made at millimeter wavelengths. So this is a radio rather than an optical image. So we can see the event horizon in this system. On the right, you can see the solar system on the same scale. So again, these are the big black holes have event horizons which scale with mass. And so the black hole in the center of this galaxy has an event horizon that's billions of times bigger than the black hole left when a massive star dies. And so a solar system scale. And it's orbiting, it's circulating or spinning at a good fraction of the speed of light. So it's a pretty phenomenal object. And all the elements of the black hole are seen. And so this system, this one system so far, but they will image more systems, including our galactic center black hole, and that data has been taken. They probably will publish it later this year. Provide our best measurements of black holes so far, most detailed measurements, the best way to measure against models of where they get their energy, as well as against general relativity itself. And there, in principle, if the observations get better, there's possibility to do some extraordinary things with these imaging telescopes and radio waves. If the light passes close to a black hole, but not in the event horizon, it can be trapped in a photon ring. That's actually formally an orbit at a distance of twice the event horizon scale. And in the theory, there are a series of narrow rings, each capturing light from all different directions, where each ring is a demagnified image of the entire universe. And each subring captures an earlier time because of the difference in light travel time. And so in principle, if you had very high resolution images of a black hole, a massive black hole like the M87 one, you could unpack the history of the universe as seen by the black hole. And this animation describes it. Now, this can't be done in practice yet. The observations aren't good enough, so this is a simulation, but this gives the principle. So what you see are the different paths of arrival of photons that are orbiting around the black hole or trapped in an orbit or deflected in the direction of our telescope. And of course, these photons are arriving from all different directions. And that's why you're essentially seeing the universe from every direction with different times, because the different orbital paths involve different amounts of time before that radiation will become part of the Einstein ring structure. So this is the kind of frontier observation that we might hope to be doing in 5 or 10 years. Can't be done yet, but with better interferometers. The ring that you saw, that image of the black hole, was done with a radio interferometer with telescopes distributed across the Earth's surface at millimeter wavelengths. Superior technology with that kind of an array could eventually produce an image like this. And from this kind of an image, there's an enormous information content. Meanwhile, supermassive black holes were found in other galaxies. The Milky Way center is only 29,000 light years away, but starting in the late 1980s, Hubble Space Telescope in the centers of apparently normal galaxies nearby, within tens of millions of light years, and found dark masses in essentially all of them. So on the left, you see the slit of a spectrograph dropped across the M84 nucleus. And on the right, you see the spectra, spatially resolved spectra, showing high deviations towards short and long wavelengths close to the nucleus. And that velocity spread is indicative of a dark mass. And so this type of data, taken particularly with Hubble, but also now from ground-based telescopes, is a very good way of proving the existence of a large dark mass in the center of what an apparently normal galaxy. And so it seems now, very reliably, that every galaxy has a black hole, but most are not active. They're not bright, and you wouldn't know the black hole was there unless you had this kind of data. Where do black holes fit in the scheme of the universe? Well, they're not that important. They're interesting and esoteric, of course, but in the scheme, in the pie chart of the universe, which is mostly composed of dark matter and dark energy, subject to another talk, of course, the normal stuff we're made of, all the atoms, the stars and the galaxies in the universe, is about 5% of this pie chart. Black holes are 1,000 times less significant. So while black holes are exciting and they can be very large, they are a minor component of the physical universe. Radio astronomers have implicated black holes too, although the radio image of a black hole was very recent. For decades, astronomers in radio arrays have been showing that the centers of some galaxies seem to have very high activity that sends jets of plasma. In this image, you're seeing radio plasma ejected to a distance of 200,000 light years from a galaxy. And the inset shows what we imagine is there, a spinning black hole accreting matter in its disk and sending out jets of plasma along its poles. So radio galaxies have been known for half a century, and we think they're examples of black holes too. And in general, black holes are gravitational engines. So the irony of black holes is that although the black hole itself and on its own is dark, black holes are the bright objects in the universe. Most galaxies have black holes that are dark. Only about 1% of the galaxies are in an active phase, where they're actively gathering gas and dust from the central regions and accelerating it and putting out radiation across the electromagnetic spectrum. But when they do so extraordinarily efficiently. So quasars, which are the brightest of these active massive black holes, can be as bright as about 1,000 trillion suns, 10 to the 15 times the luminosity of the sun. And compared to the sun, which gets its energy from fusion with an efficiency of a little under %, black holes turn mass into energy with 40% efficiency. So black holes are the most efficient energy sources in the universe. And the source of their energy is gravity. They're gravitational engines, getting their radiation originally from gravity power. Here are massive black holes. So they are extraordinary objects. The physical state of supermassive black holes is actually quite interesting because the size of the event horizon grows with the mass of the black hole linearly. And that means the density grows more slowly than the mass. And that means that the most massive black holes actually have rather low density within the event horizon, whereas a star like the sun would have that incredible mass crushed into a few kilometers size. So it was obviously much higher than nuclear matter densities. The density of mass within the most massive black holes in the universe is actually less than the density of the air that any of us are breathing. So they're not physically extraordinary in that sense, and yet they do fit the definition of black holes. The next step forward in black holes happened a few years ago in 2015 with the detection of gravitational waves, the spectacular success of the LIGO project, the Laser Interferometer Gravitational Observatory, which in its current incarnation with increased sensitivity will soon be detecting about one black hole merger every week. And what you see here is the first black hole merger detected. And it is the space-time ripples from the merger of two black holes about 1 billion light years away. And this opens up a brand new window on the universe because we can now see with gravity eyes. But also along the way, it demonstrates beyond any doubt, if there were any doubt, that black holes exist, because only merging black holes can produce this totally characteristic signature in gravitational waves. What LIGO is doing is looking at incredibly subtle space-time ripples. The animation on the left is a visualization of space-time, which is of course invisible, showing just a metric marker of that space-time as a gravity wave would pass through it. And you can see that gravity waves distort space-time in every sense, both they are compression and rarefaction waves, transverse and longitudinal, so all sorts of stretching of space-time. And the schematic of the LIGO detector on the right, which is highly amplified, of course, because these effects are very, very small, shows that when a gravity wave will pass through this physical instrument, which is 5 kilometers long on each arm, it will stretch the instrument itself differently in the two orthogonal arms. And that very slight difference in stretching between the two arms is measured as the light is brought back together into an interferometer pattern. And that's what LIGO was designed to do. It's an incredibly sensitive experiment, the most sensitive physics experiment ever built, in fact. This is what you would see LIGO closer to the optical. And all these distortions, of course, in space-time are real. Here is what the gravity wave detector sees. This is a visualization with the supercomputer's accurate physics of the gravitational wave that's And here you can see a number of the LIGO detections pulled together into an orrery, astronomical orbits. And below each one, you can see the trace, the crescendo as the black holes merge, and then a sort of ringing afterwards as the merged black holes settle down and a smaller amount of gravitational waves are produced. So we now have over 20 black hole mergers measured by LIGO. And like I said, we're expecting a much improved event rate later in the year. LIGO has also detected neutron star mergers and other compact phenomena, but we're talking about the black holes at the moment. And then we have to worry about the fate of matter in black holes. Black holes always have an ominous cast in the popular culture.
Believe me, I've been waiting a long time for someone like you to record this moment.
Thank you, Doctor.
Then I'm ready. Ready to embark on man's greatest journey.
Certainly his riskiest.
The risk is incidental compared to the possibility to possess the great truth of the unknown. there. Long-cherished laws of nature simply do not apply. They vanish.
And life?
Life? Life forever.
Well, that's a Disney movie from 40 years ago, but what do we really say about the fate of someone who falls into a black hole? Indeed, if you fell into a black hole left behind from the death of a normal star, a massive star, fate would be quite unpleasant. Spaghettification is the technical term for it, because you'd be the tidal force, the differential gravity essentially across your body, stretch you to death at all different scales simultaneously. So at the level of muscles, bones, tissues, even individual molecules. And there is simply no way anyone could survive passage into a black hole. But interesting things happen if you do this calculation for more massive black holes, just as the density of more massive black holes becomes quite modest. Once you get over about 1,000 times the mass of the sun, and there are plenty of black holes that massive, the tidal force actually goes down, even though the gravity, of course, is going up, but the differential or stretching force is reduced. And beyond that mass, it would technically be possible to survive the passage into a black hole. Now, as seen from afar, according to that early animation I showed where time slows down, time would slow down asymptotically. So it wasn't entirely fanciful in that film to say life forever. Because if you fell into a black hole, as seen from afar, you would appear to be frozen on the event horizon. Your light would be dimmed and reddened by the gravitational redshift. Your clock would be slowed down to a crawl and then to a stop at the event horizon. But you would live forever by that reckoning. To your own reckoning, however, you would pass through the event horizon to an unknown fate. So, in principle, and possibly in some far future scenario for humanity, people might actually be able to do the experiment of venturing into a black hole. But you wouldn't be able to come back out. So this is the actual astrophysical calculation. So this is general relativity now, not a cartoon. This is general relativity saying what would happen on a spiral trajectory towards the event horizon of a black hole. This is what it would look like if you could do this experiment. Thing we must consider, is it possible to make a black hole? In principle and in theory, black holes of any size can be made. So compress the Earth to a few centimeters, it's a black hole, or compress smaller amounts of matter to suitably small sizes and high densities, you can create a black hole. And this led to the speculation, which became fever pitch in the press 5 or 6 years ago, that possibly our technology, our lasers, our particle accelerators, like the Large Hadron Collider, could actually make a black hole, after which it would fall to the Earth's core and eat everything. So this idea of making a black hole through our technology has been out there for a while. It was actually always implausible. So our technology, just to put a point on it, is orders of magnitude away from creating the density appropriate to a black hole. But the public was sufficiently concerned, especially in Europe, that the physicists at CERN actually had to write a technical paper and then a series of press releases to reassure the public that CERN was not going to create a black hole that would destroy the Earth. So this issue of creating a black hole through our technology is perhaps still on the table, and maybe at some future date we would be able to make black holes, miniature ones, and study them directly in the lab, which would undoubtedly advance our knowledge. Meanwhile, black holes do have a role in the future of the universe, in the long future of the universe. Basically, beyond about 1 trillion years from now, as far as we know, the universe will continue to accelerate in its expansion and dissipate and diffuse. The radiation of the microwave background will cool, and eventually all the light from stars will be dead. So stars will be dead and be stellar remnants, and there will be no more lights in the universe. The universe will go dark. In this dark, dissipating universe, the energy sources that some future civilization, hypothetically, probably not us, but some other future civilization, how would they live without stellar energy and fusion to power their civilization, as we do, indirectly? Well, you actually can use black holes to harness energy. It would be quite easy to position yourself near any of the black holes in the universe and extract their rotation energy by sending in and retrieving probes with suitable trajectories. Because all black holes are spinning, since they form from objects with angular momentum. And so you just tap the angular momentum energy of a black hole to power your civilization. And this would take you quite a long way, up to about 10 to the power 50 years. But then, of course, the black holes start to evaporate. And as the black holes, the mass of the sun, evaporate, the longest black holes to live will be the most massive ones. So eventually black holes will evaporate, and the last black hole standing will be one like M87's black hole, billions of times the mass of the sun. And in the theory and technically, their lifetime is about 10 to the 98 or 10 to the 100 years, some fantastic, almost inconceivable amount of time. So in this universe where you've tapped the rotational energy, and even the modest black holes like the sun, dead sun black holes, have all evaporated into feeble radiation, how could a civilization live? How could there be life in the universe? And the answer is you develop a version of a Dyson sphere, because the Hawking radiation will still be there, a feeble amount of temperature. And that's all life is doing anyway, even with the sun. It's just tapping the energy difference between the sun and the earth, and the thermal radiation is life's waste product going back into space. So normally it's a sun and a cold sky, but in this future, black waves, it'll be a microwave sky that's a little warmer than the Hawking radiation from black holes. And so we can imagine Hawking radiation Dyson sphere trapping it, and the amount of energy is about a kilowatt. It's not very much, but energy's efficiency will be very high in the far future. So we can imagine that civilizations will persist. And so this is a strange vision for the very far future universe. The last civilization, the last possible living entities in the universe, 10 to the power 100 years from now, warming their hands metaphorically by the last black hole in the universe, looking at each other and saying, 10 to the 100 years, we had a good run.
All right, thank you very much, Professor Impey. That was a very engaging talk, even if the note it ended on was a bit existential.
Yes.
But thank you for that. Space is always a little bit existential. So we have a bunch of questions for you. Thank you to everyone who put questions in the Q&A, and feel free to continue asking them as Professor Impey answers them. Professor Impey, you can either open the Q&A panel yourself, or if you'd like, I can read them out.
I've got it open.
All right, sounds good.
Right. So about matter being, if matter cannot be created or destroyed, what happens when it enters a black hole? It maybe it's lost to the rest of the universe, essentially. The event horizon is, as I said, a sort of information membrane where information trapped inside and we don't know anything about it. So we can't really talk about the state of matter or radiation or any object that falls into a black hole. It's unknown to us. The theory doesn't really suggest very much at all. The theory talks about this information barrier, the event horizon, and it talks about the fact that the matter will likely fall towards the center where it's crushed into a singularity. And that's problematic for the theory, as I mentioned. So we're in an area of uncertainty, talking about what happens to matter in a black hole. Our next question is, could objects orbit a black hole, such as a planet or an asteroid belt? Yes, definitely. There are stable orbits around a black hole. I mentioned there's a bizarre orbit around a black hole, which is twice the event horizon scale, which is called the photon sphere. And that's a strange place where photons are trapped. They're not lost into the event horizon. They're literally trapped in circular orbits and will just loop around endlessly around the black hole. A little further out from that, obviously, you could have physical objects like a planet or an asteroid around the black hole. The problem is we're near the event horizon, within a factor of 10 or 100 of the event horizon. The tidal forces are severe, intense. And so physical objects like planets, asteroids would just be ripped apart, shredded, turned into dust essentially. So physical objects really couldn't survive close to a black hole because they wouldn't be intact. The next question is, what is the time scale on the simulation? Yes, so that animation was showing 15 years of data on the galactic center. The groups have now obtained more than 20 years of data. And following the same stars for longer is not really helpful at this point because their orbital times are decades and some are centuries, so you'll never see them do a full orbit. What they really are trying to do with that project now is get better sensitivity, because with better sensitivity they can see more stars. So instead of having a few dozen probes of the black hole, you may end up with hundreds of probes of the black hole. And as you increase the number of probes, the odds of you getting lucky and finding one that goes behind the event horizon and is shadowed by it, or a star that actually falls in and you get to watch it, go up. And so that's the goal of that data now. It's definitely still motivated to keep doing the experiment, but you have to have better data and more stars that you can follow, and they're getting there. Do galaxies orbit around black holes? Well, in the sense that galaxies all have black holes in them, yes, because galaxies, just like stars, most galaxies are in binary or multiple systems or clusters. So we know that galaxies have grown in the universe by mergers and acquisitions. So galaxies have grown hierarchically from small dwarf galaxies early on in the universe to larger, more mature galaxies like the Milky Way and so on. And since all these galaxies have had black holes in their centers, in that sense, yes, galaxies have black holes and they orbit each other, because as galaxies merge, the black holes will merge, and that's how the black holes grow, simply by addition of the masses. For example, the Milky Way, with its 4 million solar mass black hole, will eventually merge with Andromeda galaxy in about 4 billion years. Andromeda has a more feeble black hole, but those black holes will orbit around each other for a while, a few 100 million years, and then will coalesce and merge as the two galaxies around them merge to form what will actually be a giant elliptical galaxy. So we can't see this happen in real time, but we know that it does happen. Is there a black hole at the center of every galaxy? You can't be absolute about this. I will just say that in every galaxy where we've looked with sufficient sensitivity, yes, there is. There have been a few claims in the literature of galaxies without black holes or whatever, and they haven't all been shot down. There's a general correlation between the mass of a galaxy, especially the old stars in a galaxy, and the central black hole that it contains. So given that correlation, we know pretty much what black holes to expect in what galaxies. And we only have the sensitivity to drill down into the nuclear regions of galaxies within a few tens of millions of light years of the Milky Way. So we can't do this experiment of looking for black holes in apparently normal galaxies for all galaxies. We can do it for hundreds, and for those, yes, we see black holes. It's much harder for the many millions and billions of galaxies in the rest of the universe. So we can't say for sure that every galaxy has a black hole, but pretty good statement so far. Crazy idea. Can we make big biomechanical black holes inside our body by compressing large enough mass to the size of a single atom? Can we put a black hole inside of our bodies to, say, treat diseases? So the idea of miniature black holes, it's still on the table as a physical possibility. Compress matter sufficiently. To make a tiny black hole, say from a physical object like take a kilogram weight, you would have to compress that to about the size of an electron or smaller to make it formally a black hole. So yes, in principle, mechanically, you can create a black hole that's very, very tiny, size of a subatomic particle, from a physical object that's the size of us. We just have no way of doing that with our technology. And then if we put it inside our body, or it existed, by Hawking's prediction, it would evaporate very quickly. So the Hawking evaporation rate and timescale increases inversely with the size of the object. So the biggest mass black holes last the longest and evaporate the slowest, and the small ones evaporate the quickest. So if you could make a very tiny black hole, it would evaporate very quickly, a fraction of a second. So it wouldn't really be useful to do anything with. In terms of experiment, the idea is that the universe may have created microscopic black holes in the early phases when the density of the universe was high after the Big Bang. And these are called primordial black holes. So that's a prediction out of theory for cosmology that nobody's able to confirm yet. So primordial black holes, these small mass black holes that persist at much smaller scales and masses into the present universe, could exist. They can't explain the dark matter, as an aside. They're not sufficient to do that, but it's very hard to detect them or even rule them out. So that idea is just sitting there, which is hard to confirm. When we detect gravitational waves, how are we able to pinpoint just where in space those waves originated and the objects that merged to create those waves? And that's a good question, because gravitational wave detectors do not have very good spatial sensitivity or resolution. So LIGO has 2 detectors on the opposite sides of the continental US in Washington State and Louisiana. And LIGO now operates in concert with the Virgo gravitational wave detector in Europe, and there are other detectors coming online in India, in Brazil, and Japan, actually. So there's going to be a network of gravity wave detectors. When we have that network, we'll be able to pinpoint the direction of origin of the gravity waves better. But at the moment, gravitational instruments are not like telescopes. They don't pinpoint gravity waves very accurately. What we try and do with black hole mergers, or especially works better with neutron star mergers, is look for electromagnetic radiation that results from the merger. So if you know when a black hole merger, if you can get other wavelength telescope pointing at that part of the sky at the same time as the gravitational waves are being produced, then you have a chance of getting much more accurate positional information. So we've never really done that with black hole mergers, but with neutron star mergers, that's happened a few years ago and has become a very exciting new field of astronomy. So all we can really do is say, from just pure gravity wave detection, all we can really say is a general area of the sky, really quite a large area of the sky, and we can say the distance. The waveform tells you the mass of the objects, and the strength of the gravity waves tell you the distance to that object. So we can say it's 1 billion light years away or 2 billion light years away, but we don't know what galaxy it occurred or where those black holes actually were. Is space-time continuous in a black hole, or does it become discrete inside the black hole? Well, that's an important question, and it's just, we don't know. The black hole event horizon is a veil over our knowledge, basically. So all we can rely on is what the theory might predict. And the theory is essentially mute on this issue. So it's not clear if space-time is discrete inside a black hole. In unified theories of nature, which try and unify gravity theory, general relativity with particle physics, often space-time does become discrete. But these are speculative theories that are not tested at all, and they're not tested in a black hole either. So unfortunately, this is a question we simply can't answer at the moment. Currently, are the main challenges with imaging due to image processing, computation, or hardware limitations? At the moment, the main limitations are, they're due to the sensitivity. I don't think computation or image processing are limitations. They have quite sophisticated algorithms. There are more limitations in sensitivity of the hardware, and in particular, in 2 forms. For these radio observations, millimeter observations, you need very high sensitivity, very low system temperatures for your radio telescopes. You need extremely sensitive detectors. So there is improvement to be made in those detectors. The other improvement you can make is to make your array bigger. And the array, of course, is a set of distributed telescopes across the world. The way you could make that array bigger is to use orbital millimeter telescopes to increase the baseline beyond the Earth size. So that's being planned for the next couple of years. That would be the biggest advance, because that would increase the angular resolution, or the scale, or the fineness of scale that these images would have. What are the wave equations that gravitational waves obey? Do they come from general relativity? Yes, they are directly a prediction of general relativity. So in general relativity, when you have any mass configuration that changes. It doesn't have to be as dramatic as a merger of black holes. It can just be a dying star, supernova, that explodes and it has a central collapse. Again, it could happen in the Big Bang that gravity waves come. So you just put into your theory, and actually generally you have to model it in a supercomputer, the configuration of the mass and how it's changing, and the theory will say what strength and type of gravitational waves you'll get out. And it was by matching the merger of a binary pair of black holes is a nice, simple, relatively simple calculation. And so it's the perfect match between those simulations and the waveforms that we saw from LIGO that made people very confident that they were seeing black hole mergers. How quickly do gravitational waves travel? Is it at the speed of light? It's a good question because yes, in theory and in general relativity, it is at the speed of light. Gravity travels at light speed. But if you ask, is there direct experimental confirmation of that? The answer is no. Because if you think about it, it's very difficult to switch gravity on and off experimentally and then see how fast that signal travels. So at the moment, it's more of an assumption than an affirmation of general relativity that gravity waves travel at the speed of light. However, in all the observations we have so far, there's no evidence that it does not travel at the speed of light. Is the energy requirement the primary limitation for achieving human-made miniature black holes? Yes, it's a phenomenal amount of energy that is required to focus matter and compress it to this scale. I mean, a large hadron collider has the energy usage of a moderate-sized city, and that is failing by orders of magnitude from producing black hole density. So you can sort of scale up the math and realize that you need the energy requirement of a large country to even in principle produce a miniature black hole. So it's really, yes, an energy requirement. Is there, or is it theoretically possible for there to be an opposite of a black hole, a white hole, in which light and energy exudes from it, but matter is not pulled into it? So it's a hypothetical from relativity that is allowed by the theory, and very prestigious astrophysicists like Kip Thorne at Caltech have written technical papers and popular books that talk about white holes. So a black hole could possibly be a portal in space-time to another place far removed, but accessible through a wormhole, where on the other side the energy is coming out. The energy that's lost in the black hole on one side comes out of a white hole on the other side, two disparate locations in space-time. That is allowed by the theory. There's no evidence from astronomy or from observation that this situation arises. And in fact, to do this, you would actually have to have some very convoluted space-time that would allow disparate regions to be pinched together and connected. And the global curvature of space in the universe is mostly flat. Black holes represent very localized regions of curvature, but we don't have any evidence that white holes exist. Does the electric or magnetic field also curve inside the event horizon? How do we measure the charge of a black hole? They're both good questions. Yes, the magnetic field that a star would have is of course trapped and entrained with the black hole. So in principle, it threads the black hole in the event horizon. We can't, again, theory is required to make a vague prediction. It's not a very good prediction even about what the magnetic field might do inside the event horizon. And I would say it doesn't make a very firm prediction, and certainly not one that we can test. Black holes, because they are accreted from neutral matter on average, they do not generally are not predicted to have net electric charge. So we don't think that black holes have electric charge. Is it possible for humans to create gravitational waves here on Earth? In principle, of course, but it would require us to be able to manipulate mass in a fairly dramatic way. I mean, if we could do that technology experiment of creating a miniature black hole, that act would create gravitational waves, just the act of creating a black hole. We're very, very far short of doing that. And so in any operational sense, we're far from creating gravitational waves, for instance, that we could detect, because we can only detect gravitational waves from big black holes out in the universe. So the no hair or hair theorem for black holes, it's not resolved essentially. The hair-no hair theorem is the idea of whether black holes have properties, whether the event horizon is a naked surface that has no other properties, or whether there's other properties or aspects attached to it. And it's unresolved because theories point in either direction. There are about 100 papers a year written on the external properties of the black hole, the no-hair theorem, the information paradox, firewalls, etc. So it's a very active area of theoretical speculation, but nobody's found an experimental way to distinguish these hypotheses. Are there theories that say our universe is similar to a stem cell in a body from which new universes but often are created? Well, there's an idea in cosmology that our universe was one of a set of universes, since inflation suggests that our universe was once the size of a quantum scale event, and that if our universe was quantum genesis, then from that precursor state, which is very hard to physically understand because we need a unified theory of gravity and quantum theory, you could imagine other physical space-times being created. And so that's the idea of the multiverse. That's the idea of parallel universes. So that's a very speculative idea that does sit somewhat naturally from inflation idea in cosmology. But there's no, and there's certainly no evidence to support it yet, nor is there evidence that our universe, after it's created and expanding, hives off or spins off other universes. We've not seen any evidence of that. Does general relativity suggest the possibility of reflecting gravitational waves? What about other manipulations like we can do with other waves? That's an interesting thought because yes, they are waves. They're not the same, of course, as light waves or sound waves. They're not like electromagnetic radiation or compression in a medium as with sound. So they do have different fundamental properties. But yes, in principle, gravitational waves could be reflected from a mass. We have just struggled and been incredibly lucky and successful to have been able to detect them for the first time anyway. So we're not quite at the level of being able to manipulate these waves. We're just at the edge of detection, basically. It's a very young field. It's only a few years old. Maybe in 20 or 30 years, we'll be more ambitious in what we can do with gravitational waves. Is the X-ray emitted from a black hole perpendicular to the accretion disk created around the black hole? Well, the X-rays actually come two different ways. So the accretion disk is the swirling infalling material, and in the act of swirling and infalling, the gravitational potential energy is converted into kinetic energy, and so the disk has a temperature of 100,000 Kelvin, hotter on the inside than the outside. And so the disk itself, the accretion disk, is emitting X-rays, soft X-rays and ultraviolet radiation. There are also X-rays that come from the very high energy particles and plasma that's ejected along the jets and the poles. So X-rays come from both parts, and that's why black holes are very strong X-ray emitters. So that's good. I think that was the last one, and it's about the time I have to leave anyway. So that seems about right. I got all the questions.
Right. Thank you so much, Professor Impey. It was great to have you here, and thank you for answering all the questions.
Yeah,
we really appreciate you being able to come out.
Pleasure to be here, and there were great questions. I appreciate those, and maybe sometime in the future we'll do this and actually get to Toronto. That'd be fun.
Oh, that would be very nice. So for everyone who is still with us, we have our next event starting in approximately 20 minutes. ASX's own Katerina will be giving an astrophotography workshop where you will learn how to take some awesome pictures of space with your own smartphone. So stay tuned for that in 20 minutes. Until then, go take a walk, grab some coffee, eat dinner, I don't know. But we will be starting the next event in